Thanks, guys. I don't think our next speaker needs much of an introduction. Vitalik Buterin, creator of Ethereum. Very professional shirt on. Excellent. Yeah, without further ado, here's Vitalik.
Yeah, so I wanted to give a kind of brief version of a presentation I've made in more academic contexts a couple of times, and this is focusing primarily on another kind of Ethereum scaling, which is basically increasing the base capacity of the Ethereum blockchain itself. Right? So, and particularly in some of the technical challenges that arise if you try to create a blockchain that goes beyond the transaction capacity that any one computer can handle. Right? So this applies to things like merge mining. This applies to any kind of multi-blockchain solutions. This applies to any kind of IOTA style system. This applies to just any kind of system that tries to create multi-blockchains, like sub-chains, side chains, like sharded chains, like just any kind of massive on-chain capacity increase, right? So there are generally several different challenges that are involved there, but as Joesph may have briefly mentioned, the data availability problem is probably one of the more serious ones. So just to kind of introduce the mathematical model here, everyone probably is familiar with what a simple blockchain looks like. You have blocks. Each block contains transactions. Anyone here not know what a transaction is? And we're going to assume that each block and each transaction is small enough, that each block is small enough that any single node in the network can still process the entire blockchain. Right? So we're going to use this kind of big O notation abstraction of C to refer to the computing power / storage / bandwidth of any individual node. And we're going to say that a simple blockchain will have a transaction capacity that's also O of C, so that the amount of computational storage and bandwidth load that any particular node incurs is also going to be O of C. Right? So this is not scalable, right? But this is a way of doing things, and it's a blockchain, and it works. Now, taking this as a starting point, there are a few incomplete scaling paradigms that work okay, but they have a lot of problems. So we'll start with the very simple one: super big blocks. So, obviously, there are always gains that you can make by just bumping up parameters, and even the Ethereum blockchain itself, we increased the capacity by about 40% recently when miners voted the gas limit up from about 4.7 million to about 6.7 million. So capacity, just simple parameter tweaks like as capacity increases definitely have their very important place. But if you try to push them far as the only scaling paradigm, then you run into this problem. If you increase the transaction capacity of a simple blockchain from C to 1,000 times C, then the amount of load needed to be a validator also goes up from C to 1,000 times C. And if in your model C is the amount of capacity that a regular node can handle, then basically what you're saying is that the only nodes are going to run in data centers. So this gives you scalability at the cost of decentralization. Here is another incomplete scaling paradigm. And this is probably the scaling paradigm that the crypto space has kind of de facto adopting, at least temporarily over the last 6 months without even realizing it. So, how many people have sent a Bitcoin transaction recently? Transaction fees are a bit high, right? How many people have sent an Ethereum transaction recently? Transaction fees are much lower, but they're still higher than they were half a year ago. How many people have sent a Dogecoin transaction recently? Well, the transaction fees on Dogecoin are a lot lower. Right? This is a scaling paradigm. So network capacity goes up from C to 1,000 times C. The validator load is still C because every single person only needs to generally runs a node on one blockchain or maybe a couple of blockchains. But so what are we trading off here? Well, the answer is pretty simple, right? Each chain has 1,000 times lower security. So if we have an ecosystem where the total amount of, let's say, mining hardware is $10 billion, then if before it would cost, let's say the total amount of mining hardware is $2 billion, if before it would cost $2 billion to do a 51% attack, if the capacity is evenly distributed, then the cost of a 51% attack goes down from $2 billion to $2 million. So getting scalability, keeping decentralization, but sacrificing security. Now, merge mining. So this is a kind of proof of work only approach, but the general idea here is that you have 1,000 altcoins, but miners can mine many of them at the same time. You know, the problem is this is actually basically just like a pick and choose between the last two ideas. So if every miner mines every single altcoin, then what you really have is you still have a system where the required capacity of a node is basically 1,000 times C. If every node mines or every miner mines on every altcoin, then to be a miner you would still need a data center. Or if you don't have that, then if each miner only mines a few altcoins, then you still have fairly low security. So this doesn't really help us all that much either. Right? So I claim that there is this sort of fundamental scalability trilemma, which, while not impossible to overcome, is very hard to overcome. And it says that a blockchain can only have two of the three following properties that I define as follows. The first property is decentralization. And here I define decentralization as the blockchain being able to run in a way that only relies on basically guys with regular laptops. Right? So no reliance on like large-scale data centers, and especially no needs to trust people with large-scale data centers. Scalability. And scalability I also define in this kind of asymptotic way that should be familiar to people with core computer scientists. So basically the ability to process more than OFC transactions. So the ability to process some number of transactions that's super linear in the capacity of a node. In security, basically being secure against attackers with up to O of n resources. So with up to a quantity of resources that's proportional to the amount of economic activity in the entire chain. So with regular systems, this proportion is either 33% or 50% of the attack of the nodes running the consensus. If it goes down from 33 to 25%, that's fine. But what we can't do is have a system where basically the more the scalability goes up, the lower the bound goes. Right? So this says that it has to be secure against at least some fraction, and this says the transaction processing has to be super linear, and this says, well, we can't have it's super linear in the capacity of each node that the system depends, each individual node that the system depends on. And having a system that actually has all three of these properties is like very much not easy. Now having two of these properties is very easy. So for example, if you want decentralization and security, then this will be satisfied by any existing blockchain. If we want decentralization and scalability, 1,000 altcoins. And if you want scalability and security, then super big blocks, right? But if you want all three at the same time, then life becomes much harder. Now, before we get into data availability itself, I'm going to take a bit of a detour into a concept that's been researched in Ethereum land for a while, but which is called interactive computation. And the setup here is as follows. Suppose that we have some function, and this is a function that we want to calculate, and we want to use the blockchain to ensure that we calculate a correct answer, up to some cryptoeconomic bound. So basically, either we get the correct answer, or the people that force us to get the wrong answer lose a huge amount of money. Now let's say this function f happens to be a function which is decomposable in this way. So we can represent f as this composition, fn of fn minus 1, off the dot, of f3, of f2, of f1. So we have basically have like a number that's being strung through all of the f's, and at each intermediate step the number is still fairly small. Right? So one example of this kind of computation would be take a number, hash it 1 billion times. Another example would be take a number and run a time log function of that number 1 billion times. Now, the kinds of functions that are not represented here are any situations where kind of the intermediate states can be very large. And so, for this particular case, how do we try to compute this function on the blockchain? Now, the problem is we can't compute all of f because, well, we'll assume that like the total computational cost of f is O of c squared, right? So we'll assume that f itself is so large that it cannot be computed on the blockchain in its entirety. So here's what we're going to do. The submitter is going to send a bunch of interactive states of the computation. So anyone can say, hey guys, I have a solution. And he's going to submit a bunch of values. S1, S2, S3, blah, 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 all going all the way down to Sn. S1 is going to be X after applying F1. S2 is going to be that result applying F2, and so on and so forth. So basically, kind of at each layer of the onion, you would provide the intermediate value. So then the submitter submits all of these values, and the submitter also submits those values along with a deposit. So the deposit basically says, here's a pile of ETH. If someone can prove that I did something wrong, you can have my ETH. Now, if you can't, so the idea that we're going to go after here is, if you can't prove that the submitter is wrong, then, or if no one proves that the submitter is wrong, then that means that the submitter is probably right. And so this is the general idea around what we call interactive computation. Now, if we want to see the kind of performance of this kind of system, then as I mentioned, this big F is going to be is going to have complexity O of c squared, and we're going to let n be O of c, right? So each individual Fi is also going to have like O of c computational cost, so which means that it can be computed within one transaction. So in Ethereum land, it fits within 6 million gas, and the number of these Fs, it will be small enough. Well, it has to be small enough that it can also fit within a transaction. So that's another O of c limitation on the number. So O of c times O of c gives us the O of c squared limitation on F. So let's see what the rest of the game looks like. After a submission is made, there exists some challenge period. Could be an hour, could be a day, could be 5 minutes if you're really daring that way, but you'll probably want more. Within the challenge period, anyone can submit a challenge index. So anyone can submit a number. So it basically says, hey, I looked at what you're doing, and I think at position 43 you're wrong. Now, well, so the challenger would send a transaction, and this transaction would basically call, the function challenge of some smart contract, and as its argument, it would have like I equals 43. Now, what would the function do? It would try to verify the challenge. And the specific way it would verify the challenge is, when the submitter sent all these values, the function would save S1, S2, and so forth. So what it would do is it would look up the value of S43 that was saved, then it would apply F44, and it would check the result F44 applied to S43, and it would check whether or not that's equal to the S44 that was supplied. Right? So basically, the idea of the pointer is to point to a specific place in this particular list and check, in this particular place in the list, was the computation actually computed correctly? If it was, then the challenger just wasted a bunch of gas. If it wasn't, then the challenger gets some portion of the submitter's deposit and the solution is wrong. If no successful challenges are made within some period, then the submitter gets the deposit back and they also get a reward. Right, so this is kind of the basic idea behind interactive computation. Right? Now, as it turns out, if you want to extend this further, so if you want to extend this from O of c squared to roughly O of 2 to the c, then you can do a multi-step game. And you basically in this multi-step game, you would just have O of c rounds. And if you wanted to have the state be have intermediate states be larger than a small number, then you can do that. And the way that you would do that is you would basically have the function operate over a Merkle tree, and each individual kind of record of a step would just have to include some Merkle branches that basically say, here is the portion of the state that I'm modifying, here's what I'm modifying it to, and here are a bunch of Merkle proofs that prove what I'm doing is correct. So there are ways to kind of extend this and make it fairly powerful, right? So, all hail the Merkle tree. Bow to the might of the Merkle tree. Why is no one bowing? Okay. You know how many gigabytes of bandwidth that guy saved you? Anyone who's ever run a Geth light node, pay more respect to the guy.
That's a YouTube.
So basically the idea, Merkle trees allow for efficiently verifiable proofs that a hunk of data is, that one particular hunk of data is part of a much larger hunk of data, which is represented by a much smaller hunk of data called a root hash, right? So if I have a really huge hunk of data, I can make a Merkle tree out of it, then that Merkle tree identifies that big hunk of data with a hash, and if I want to prove that any particular piece of data is actually part of the data set represented by that hash, then what I would do is I would just provide a bunch of, I guess, very small number of hashes, and this would prove that the value that was at one particular position in that piece of data actually is some particular piece of value. And if hash functions are collision resistant, then it's unforgeable, right? So, yeah, great guy. Ethereum uses Merkle trees both for the transaction tree and also to Merkle Patricia trees to keep track of the state and including the account list and the storage of each account. So, like, Ethereum is a light client protocol and Ethereum's fast syncing. So not just a light client, anyone who's ever synced a Geth node, like, or a parity node for that matter, you really got to thank the guy. Yeah, so basically what Merkle trees let us do for interactive computation is, once again, they let you take this kind of mechanism that works well when every intermediate state is a small value, and they let you kind of abstract the mechanism a bit, and if you require certain participants to provide Merkle branches in a few places, so a Merkle branch just being these sets of hashes going down from the root to a particular value, then they can do the exact same thing for even computations where the intermediate states become arbitrarily large, so like larger than O of c in size. So that's if you just want to verify program execution on the blockchain, right? And that's the sort of thing that, for example, TrueBit is doing. Now, this is also something that can be used in a blockchain, right? So we can make a bit of an analogy here. And the analogy that we're going to make is that processing the blockchain actually is this kind of function, right? And in fact, all of these f's are the same. X over here is always the genesis state, right? So if anyone here bought Ether in the Ethereum token sale, then you are part of the genesis state. Remember that? Now, then this is like the function for verifying the first block. And the output of the function for processing the first block is the genesis state plus, well, there weren't any transactions in the first block, so it's basically just a 5 Ether mining reward. Then you have F2, which is processing the second block, F3 processing the third block, going all the way up to roughly, like 4.29 million for processing the last blocks today. Right? So a blockchain is kind of a serial function that works in this way. But so you can think about this exact kind of interactive computation as being a mechanism that you could use to verify a blockchain. Now, obviously, with one of the differences between a blockchain and a regular computation is that blockchains have a lot of auxiliary data, right? So if you can imagine everyone having all of the block headers, then if he wants to process a block header, then you would need a bunch of auxiliary data. So the first piece of auxiliary data that you need is the actual transactions that went into a block. So like if someone has all the block headers, then they have the headers, but they do not have the actual transactions. So if he wants to actually process a block, they need the transactions. And the second thing is, in order to process each individual block, they would need the Merkle branches of the state representing the specific accounts that were modified during that block. So if there's a block, and for simplicity, this block contains, let's say, one transaction, and this one transaction sends one ether from me to someone else, then the auxiliary data is, first of all, the one transaction, and second, with that one transaction, you should be able to show that the one transaction actually corresponds to the root of the transaction Merkle tree. And the second thing that you would need is the entries in the state root. So the entries in the state tree that correspond to basically the three accounts. One of them is the account I'm sending from, one of them is the account I'm sending to, and the third account is the miner of the block. And if you have these things, then you can actually verify for yourself that if you get a block plus all of these proofs, that basically whether or not the block header is valid. Whether or not the block header, which says, here was the previous block, here is a Merkle root of the transactions, here is the new state root, whether or not the new state root actually is the root hash of the new Merkle tree of the state that results from executing those transactions, or whether that it's some completely different value. So now what does this mean, right? Basically you can think about trying to do a kind of interactive computation-like mechanism here. If let's say you're a client, then you could download every block header. If you doubt any particular block, or if, let's say, someone in the network finds fault in any particular block, so let's say they think that, oh wait, this block looks like it actually computed the state incorrectly, or this block looks like it contains an invalid transaction, then what they can do is they can give you a bundle, right? And the bundle would consist of basically a bunch of Merkle proofs. So Merkle branches for the transactions, Merkle branches for the portions of the state that get accessed by those transactions, and then you can use those Merkle branches, and you can verify for yourself, does this old Merkle root plus these transactions equal this new Merkle root? If it does, then it turns out the block is valid after all, and if it doesn't, then basically you've just verified a proof that that particular block is invalid. So you can think, so you could see how, like this kind of mechanism, and you can think about these kind of bundles as being, they're basically called fraud proofs, as being one kind of way by which a blockchain, where that blockchain, like with a few adjustments, might have substantially more than OST transaction capacity, could still be verified by a node that has only OST resources, because the node does not verify most blocks by default. The node just downloads the block headers, by default accepts the block headers, and only if there's fraud proof does the node actually try to download all of this auxiliary data and verify for themselves that everything is correct. So this kind of looks like it might be feasible, right? But it turns out there's a major problem. And the major problem is data availability attacks. So this is the slide that I had at the beginning of the presentation. So here you have a Merkle tree, and most of the data in the Merkle tree we can see, but there's one piece here that we can't see, and Casper the Friendly Ghost is afraid. So basically what is going on here, right? So the attack here is simple. Let's say that a malicious miner publishes a block. This block could be valid or it could be invalid, right? But the miner publishes the block header, and the miner publishes most of the transactions in the block, but the miner leaves one transaction out. So this transaction could be a valid one, it could be an invalid one, but the miner just decides, I'm going to keep this piece of data to myself. I'm just not going to broadcast that part, right? So the problem then is, well, this is still a problem, and can clients actually effectively detect this? So, first of all, what can data unavailability attacks do? Now, the one thing that, if a data unavailability attack is successful, then one thing that they could do is they could convince the network to accept an invalid block. And the reason is that there's no way to prove invalidity, right? Until this piece of data is published, there's no way to tell whether this transaction is A, valid, or B, an invalid transaction that sends 10 million ether from all the major exchanges to my own wallet. So, it's just data. Like you can't see what it is, and like sure there's a hash, but it could be a hash of anything. So this is a problem, right? Now, let's say that we are in like ideal crypto magic world, and we have super effective zero knowledge proofs. We have Starks, we have Snarks, and they have it's Magic Fairy La La Land, and they have no trusted setup. We're totally happy with their crypto assumptions. They're practical to verify. Everyone uses them, and so a Stark gets attached to every block, and so we can prove that any block is valid, even if the data is not published, right? This is all theoretically possible, but even in this kind of world where we can use zero knowledge proofs to verify, or succinct zero knowledge proofs to verify validity, data availability is still actually a huge issue, and it's a huge and a successful data unavailability attack would be a huge problem for two reasons. So the first reason is that basically a successful data unavailability attack prevents the world from just knowing about what the real state is of some particular account. So let's say that I have this hidden transaction is myself interacting with the DAO. And the DAO is this a huge decentralized thing on the blockchain that has let's say in this parallel world still has 10 million ether in it. If I send this transaction and I include or if I create a block that includes this transaction, but I do not publish this transaction, then effectively, even though the world knows that everything is valid, the world now has no idea what the state of the DAO is. Right? I've basically prevented the world from just having that knowledge. And particularly what this also means is I've prevented anyone else in the world from having the information that they need in order to make their own transactions that interact with the DAO, or possibly even make their own transactions that interact with any account that I've touched. Right? So the problem is, right, that if I wants to make, like in general, if you wants to make a transaction and you wants to prove that this transaction is correct, like in any kind of cryptographic system, you don't just need the Merkle root, you also need a witness, right? And in this case, the witness is Merkle branches. In some other system, the witness could be something else. But if I can prevent you from, everyone from learning the data, then basically I can just prevent them from having the data that they need to be able to construct the correct witness. So in an Ethereum scheme, like if I give you a state root and suddenly some data in the Merkle tree is missing, then no one can make Merkle branches to that anymore. In a UTXO scheme, well, you can't, basically other people have no way of knowing that there was not a transaction that spent any particular UTXO, and so therefore there's no way of proving that any particular UTXO is still unspent. So these, basically, even if you can guarantee total validity, successful data unavailability attacks are still fatal. And this is why zero knowledge snarks and starks or any crypto magic by itself is not going to solve the availability problem. So here is the kind of fundamental data availability problem. Incorrectness can be proven even to a light point, right? So we have this notion of fraud proofs. And so if there is a transaction which let's say sends 100 ether from me to some address, like let's say the DAO. But I try to create a block, an invalid block, where in the state of the invalid block, the result is that it sends an extra 5 million ether to myself. Then this is an example of an invalid block, and so this is a kind of fraud that can be proven. Like with Workable branches, you can even prove the fraud to a lifetime. Data unavailability cannot be proven. And the fundamental reason behind this is this. Fraud, a simple fraud is a uniquely attributable fault. Data unavailability is not a uniquely attributable fault. Now, what do we mean by this? Basically, this is a special case of something that I often call the speaker-listener fault equivalence dichotomy. And in this case, in this particular case, it looks like this. So here is kind of real case one. So this is one possible description of the state of events in some real world. We imagine that at time t1, we have evil validator 1. Evil validator 1, so this could be a miner, or it could be a proof of stake validator, or it could be anyone, publishes a block with missing data. At time t2, validator 2 raises an alarm. So they make some kind of message, and this is very abstract, like it could be any kind of message, that basically says, hey guys, this data in the block, this particular piece of data in this block is missing. Oh no, I am scared. At time t3, validator v1 just goes ahead and publishes the remaining data. So this is world 1. In world 2, at time t1, validator v1 publishes a block with all the data. So validator 1 here is the good guy. Now here we have validator v2 who is malicious. See, validator v2 has the devil horns now. Raises a false alarm, right? So v2 is now the one that's being malicious, and he basically says, hey guys, this piece of data is missing. At time t3, v1 does nothing because v1's like, hey guys, I published a block with all the data, already. What's going on? Why are people complaining? Now, notice one particular fact. From the point of view of any validator or of any client that goes online after T3, World 1 and World 2 are totally indistinguishable from each other. Right, so in general, right, speaker or listener fault equivalence basically means that like if there's one guy who is supposed to speak and one guy who is supposed to listen, then if it looks like the second guy did not hear the first, it could have happened for 2 reasons. One of them is that the guy who was supposed to speak did not speak, and the other reason is the guy who was supposed to listen did not listen. And like this will also exist in just traditional blockchain consensus, because like not speaking would be like not creating blocks, and not listening would be censoring other people's blocks. Now, and basically like those two are just fundamentally not distinguishable from each other. And in this case, they're even more indistinguishable. Now, this then leads to the next paradox. So let's say that we define a fisherman as being this, and this is like a term of art that was created by Gavin Wood. But let's just say we define a fisherman as being someone who specializes in basically raising the alarm if something goes wrong. So fishermen go around hunting for unavailable data. So kind of like challengers in an interactive computation game, kind of like like any challengers in Truebit, basically someone who looks for this kind of fraud and points it out. In World 1, we're gonna ask a question: what is the expected return of being a fisherman? So we're gonna just ask a very generic question of all protocols: what is the expected return of being V2 in a case where this case is frequent? If the expected return is greater than 0, then the protocol has a money pump vulnerability. The reason why so money pump vulnerability basically means that what an attacker can do is they can just go around raising false alarms on random blocks that actually do have all of their data correctly published. And because case 1 and case 2 are indistinguishable, they can just go around doing that, and we've already established that they can make an expected profit. So this is bad, right? Now let's say the return is exactly 0. Now you can't money pump the protocol. You can't just extract money from the protocol by giving yourself rewards, but you still have a DOS vector, because what you can do is you can basically raise an alarm on every single piece of every single block, and thereby force everyone to download everything. And thereby, if the capacity of the blockchain is greater than OFC, then the amount of data everyone has to download is also greater than OFC, and so it's not scalable anymore. Case 3 is the expected return is less than 0. But now, this is okay in case 2, right? In case 2, this means that there's no incentive to do this kind of attack. But in case 1, it also means that in the case where there are these malicious validators publishing blocks with missing data, there is no incentive to be a challenger. And so basically then you become vulnerable to this attack, where an attacker just publishes a bunch of blocks with missing data. You might have a few altruistic challengers to challenge. The attacker just outlasts the challengers. So the attacker just waits until the altruistic challengers run out of money. And then, basically, once they all do and once they're all gone, the attacker starts doing whatever data unavailability attacks they want. So, basically, we have to choose between 3 evils, and there is no good way out. Now, it turns out that there are actually a couple of ways out, and I'll go through them very quickly. Now, one of them is this random sampling approach. So basically, in the protocol, you make an honest majority assumption. And the honest majority assumption basically says, we're going to randomly select committees, and each committee is going to look at one particular piece of data, and we're going to kind of delegate our trust to these committees. So we're going to make an assumption that the majority of what every committee says is honest. And so if there is a piece of data, and if the majority of some committee signs off on having seen that the data is available, then we treat the data as being available. So this is one solution. Another solution is that basically, this is more trustless, and it's actually very close to being fully trustless, is client-side random sampling. Right? So the idea basically is that instead of every client checking for availability by downloading all of the data, the client just basically samples 100 random transactions, sees if they can actually download the Merkle branches for all those transactions, and if all those transactions are there, then they accept the block as being actually available. So this is a strategy that lets you audit the availability of an arbitrarily large file in basically with like OF log n space. Right? Now, this works well against attackers that try to withhold an entire block, or even 50% of a block. It fails against attackers that try to withhold 0.01% of a block. Right? So if an attacker withholds 0.01% of a block, then on average, a client would need to make about 10,000 checks in order to detect an attacker. If an attacker withholds 1 transaction, then a client would have to download, on average, almost everything in order to actually catch him. So the solution to this is basically erasure codes, right? So basically, we take the original data, and we extend the data in from, let's say, 8 chunks into 16 chunks, or 8,000 chunks into 16,000 chunks, and we use fancy spooky math and to generate the extra 8,000 chunks. And the fancy spooky math has this property that any 8,000 of these 16,000 chunks are enough to basically reconstruct the entire data set. Now, if you want a proof that this is possible, I'll give you a very simple proof. Let's say the original data had 2 chunks. We're just going to take those 2 chunks, and we're going to put those 2 chunks on a line, right? So we're going to draw a line, and we're going to just put down 2 points, and we're going to encode the data in the original 2 chunks into the coordinates of the points. 2 points make a line. Now what we're going to do is we're going to extend the line, and we're going to take 2 other points on the line. Now we have a line, and you have 4 points on the line. Now, as any mathematician knows, if you have any 2 of those points, then you can recover the line, and so you can recover all 4 points. So that's basically how this math works in a kind of 2 of 4 setting. Now, if you want to go from 2 of 4 to, let's say, 3 of 6, then you can either go from a line to a plane, or you can go from a line to a parabola. And if you want to go higher, there are like ways to do that, fairly simple ways to do that as well. So this is something which is doable, and I've actually done it, and there are results, and it actually does seem to work fairly well. And so now the one kind of drawback for this kind of approach is that you actually do need another kind of fraud proof that basically says, this particular block is invalid because the erasure code is malformed, but like that's another detail and we already have fraud proofs. And in 10 years from now, maybe we can replace both kinds of fraud proofs with like zero knowledge proofs like stars. So this is basically the state of the art in terms of like dealing with data availability issues. Now, just to kind of summarize and put everything together, now you might ask, well, okay, well let's suppose that we have all these ingredients. What does a scalable blockchain actually look like? And like it's actually not that difficult to summarize, right? So basically, imagine that instead of having one blockchain, the way that we have where you have this kind of one big universe of accounts, what we're going to do is we're going to have a blockchain that has, let's say, OFC separate universes, right? So just to make it more concrete, let's say 200 separate universes. Each one of these universes is kind of like its own account space, and every block is going to have, instead of having transactions, you're actually going to have a 3-level block structure, right? So the current block structure is 2-level. So at the top you have so in a 2-level block structure, like at the top you have a block header, and then at the bottom you have a block. Here we're going to have a 3-level block structure. At the top we have a block header, and we're going to have a Merkle root, which is going to make a Merkle tree, and that Merkle tree is only going to be a Merkle tree of collation headers. Now, what is a collation header? It basically is like a block header, except it's a block header for one of these specific universes. So you might imagine people sending transactions, and these transactions only affect, let's say, universe number 84, and so they're only allowed to affect accounts in universe number 84. And then you have a collation header is basically just a header of a block that contains a bunch of transactions that are only inside of universe 84, and it contains like Merkle tree roots for the previous state and the post state of universe 84. And then you have these collation headers, and then the actual top level block is going to contain basically just a bunch of collation headers. So no node is ever going to download the whole thing, except maybe block explorers like Etherscan, right? Most nodes are only going to there would actually be 3 levels of node. So you would have the very full node, which we could call an archive node, which would be run by maybe just a couple of block explorers. Then you would have pure white clients, which would just have the top level header, and you would have a bunch of nodes in the middle, and the nodes in the middle would have the top level blocks. So they would keep track of all the collation headers, and they would keep track of all the block headers. And if there is any particular shard that there are any particular universe that they're interested in, then they would, for that particular unit, basically act as full nodes and actually keep track of all the transactions for that particular universe. To fully track any one universe, it takes OFC effort or OFC computing efforts. To keep track of the top level, it takes OFC computing effort. The scalability of the whole system is OFC squared. Now you might ask, well, how can a node that only keeps track of the top level be confident about the security and correctness of every single universe? Well, the answer is they either rely on committees, or they rely on a combination of erasure coding to prove availability and waiting for fraud proofs to prove correctness. And realistically, they can just rely on both of these mechanisms, and basically, like the scheme itself will only break if both of these mechanisms break at the same time. So this is roughly how kind of blockchain sharding in a way that's kind of as secure as I think is possible, as I currently think is possible would work. Thank you.
Can we give another round of applause for Vitalik? So we are going to have a panel discussion. So if Thomas and Joesph could come up, and Steve first.